have three Wilkinson stories, and I'm going to take a poll afterwards. How many of you heard how many stories? I bet you none of you have heard all three of them. First one was about the early days before the QR algorithm. It finds eigenvalues doing the characteristic polynomial, and so there was a lot of interest in how to find roots of polynomials. There were two competing methods, the Laguerre method and the Barstow method. And Wilkinson wrote a program that would use Laguerre method, and if it failed, it would print a message and go to the Barstow algorithm. And he had this program in the library at NPL for some time, and it never failed. He never got the message about the Barstow algorithm. He wrote that then in favor of the Laguerre method. Somebody sent him a polynomial that the Laguerre method failed. Wilkinson wrote back and said, no, it works fine. And he looked more carefully, he had a bug in his program. It didn't print the message. What was the second one I did? Oh, yeah, thank you. Yes, we saw Olga Towski there. They used to come to the University of Michigan for the summer conferences every summer. Householder came 15 years. Wilkinson came for 14 years. And Olga Towski would come with her husband, John Todd, and sit quietly. She was a kind of meek Viennese woman. And one day, Wilkinson and Varga and so on would go to the old Pretzel Bell and drink huge amounts of beer, order beer. Olga had a friend coming for lunch one day, and she asked Jim, is it possible to order beer in more modest quantities? And Jim said, well, yes, but it's never been one of my ambitions. The third one, my goodness. Oh, yeah. Wilkinson was lecturing at Argonne. You saw a picture of him there. That last picture is him lecturing at Argonne. Pete Stewart was in the audience when Wilkinson was talking about inverse iteration and how to pick the shift in inverse iteration. And Pete began to question Wilkinson about the choice of shift. And Wilkinson says, wait, if we're going to argue, I'd rather switch sides. Okay. How many people have never heard any of those stories? Oh my goodness. How many people have heard one? How many people have heard two? Anybody heard three? I didn't think so. Okay. I got some more, but anyway, later. This is just a little bit of thing. I was wondering about how to find. Wilkinson knew that when a matrix had sensitive eigenvalues, it was near a matrix that had multiple eigenvalues. And he was interested in how far away it was. And when I started to get ready for this meeting, I had a dumb bonehead method of doing it, which I won't talk about because I came across this paper by Alan Bora, Ralph Byers, who we know, and some of us know passed away very early, and Michael Overton. Some of you know Bora, I guess. She's been here. Yeah, so I don't know the first two. And there's some software that goes with this, which I'll talk about, that Overton wrote, and I've just been reporting on using that software. So I started with, last week in my blog, I had the derivation of where this matrix came from. But I'm going to be my first test matrix. Let's forget about where it came from and just start to look at its eigenvalues. If you ask to compute the eigenvalues in MATLAB, you come up with those numbers. There's about 4 digits missing at the end. There's supposed to be 1, 2, and 3 as the actual eigenvalues. But we lose about 4 digits in the computation, and that is explained by the condition number of the eigenvalues. That's different than the condition number for inversion. They're all about 10 to the third, 10 to the fourth, and they explain how much you lose during the computation. The condition numbers come from computing the left and right eigenfunctions, and you compute them in such a way that they're normalized, that the dot product of y with x is the identity matrix, and that means these are the condition numbers. That's a new MATLAB function. How many people know about that function? Yeah, and so that's a handy function here to compute the condition numbers. This is let me go. What? Oh, there. Okay. So this is the Eigenvalue, which was written under Nick's, the other Nick's.
No, he's the other Nick.
Oh, he's the other Nick. All right. And here we're showing the matrix, the intervals around the three eigenvalues coming together under perturbation and mating in a kind of typical saddle point. And it's when these exactly meet that you're able to perturb the matrix and bring the eigenvalues together. Here it is. We're going to zoom in on two of the eigenvalues, and that's where they meet, and that's the double eigenvalue there where they meet. We can get that out of Overton's program, near DefMat. Well, did I say? Yeah, Michael is an optimization guy, and this program is very much like programs that Margaret knows about that does optimization, and it prints out by default lots of information about how it's computing. This is the double eigenvalue that the two matrices where the two meet. You compute that by doing an SVD on A, and then getting the matrix B as a rank 1 perturbation of A. And there's the matrix B, it has a double eigenvalue. The eigenvalue is infinitely sensitive, and so when you compute the roots, they're not exactly equal, but that's the mating of those first two eigenvalues. And that's how far it is from the original matrix to the perturbed matrix. Wilkins was very interested in that number. The question is now today, is that unique, that nearest matrix? And that's detail about we won't go into today. Wilkinson used the Frank matrices as an example. He used the Frank matrix of order 12, but I'll use the Frank matrix of order 9 because it fits on this slide. It's an upper triangular matrix plus a subdiagonal. You'd think that the eigenvalues are close to the diagonal elements, but they're not. These are the eigenvalues of the Frank matrix of order 9, and there are their condition numbers on the right. The condition numbers are 10 to the fourth for the small eigenvalues and order 1 for the large eigenvalues. So it's the small eigenvalues that are going to come together here. We can go to Eigenvalue, and there's the 9 eigenvalues of that matrix. There's only 7 regions there. Well, let's see. That's another example. Zoom in on the small region, and there the red contour in the middle is where the two regions come together and give you the double eigenvalue. And again, this saddle point, the typical kind of saddle point. And near DefMat tells you all about how it was doing and which algorithm it was using. It's 1,000 lines of MATLAB in 9 functions, so it's a non-trivial thing to do this calculation. There's the eigenvalues of the original matrix, and on the right is the eigenvalues of the perturbed matrix. And you see that the two small eigenvalues have come together there and found their mates, as it were. This is the picture of the Frank matrix of order 9. There's the almost an upper triangular matrix. There's the upper Hessenberg form, and it drops down to 0 on the left-hand side. And there's a picture of the perturbation. The perturbation comes at the very end of the matrix, and that's what gives you the double eigenvalue. And there's how far it is. It's very close, 10 to the minus 7th. You don't have to perturb it much to get the double eigenvalue. And Wilkinson was very interested in that number and what it could be. My third example is the Wilkinson matrices themselves. We usually work with the matrix of order 21, W plus 21, but again, at the order 9 matrix fits on the slide. And the perturbations they're not as close as the order 21 matrix. Oh, I'll get ahead of myself. So it's this tridiagonal matrix with ones on the diagonal. And we know that in order for a symmetric tridiagonal matrix to have a double eigenvalue, it has to have a 0 someplace on the subdiagonal. And this doesn't have small numbers on the subdiagonal. How can it be close to a matrix with a double eigenvalue? Well, the answer is you make a non-symmetric perturbation to this symmetric matrix. There's the eigenvalues of the matrix, and the conditions numbers are all 1. That's how I got started, and we're thinking about this, is I'd heard a lot about how you perturb a non-symmetric matrix that has big condition numbers. What if they're all perfectly well conditioned? What do you do then? Here's the I-tool picture of that matrix. It's a matrix of order 9, but there are only 7 circles in that diagram. And that's because the 2 right-hand circles have nearly double eigenvalues in them. And if we zoom in on the right-hand circle way in, we're coming into the far right-hand side of that matrix and zooming in by 3 orders of magnitude. This is what the I-tool looks like. There's your nearly double root, and these regions about says how large the perturbation can be, and you see that the middle perturbation of one of the red ones, the eigenvalues are close to kissing, close to becoming mates, and we don't have to move them far to get them. Here's what near death mat says about that matrix. It's a completely different message, completely different algorithm, because it's discovered that this eigenvalue problem is symmetric, and it knows how to do the perturbation. It's actually an easy problem in how to do it, and it tells you what it does. Here's the original eigenvalues, and the eigenvalues when they're perturbed. The double eigenvalue is actually now got so they're exactly equal, but when we compute them in MATLAB, it comes out to be complex with the eigenvalues. Here's the picture of that matrix, tridiagonal matrix, with bigger elements down the diagonal, and here's a picture of the perturbation. The perturbation is way off to one side. You have to go from a symmetric matrix to a slightly non-symmetric matrix, but that one has the double eigenvalues. Okay, that's how far it is, and great interest in this computing this number. If you want to know the details about how this computing, you have to read the paper by the 4 authors and get Overton's software. Overton was a big help in me in getting ready for this talk, and I want to thank him about it. He can't be here. From Bath, Freitag. Yes, Melina Freitag. She also has other software for finding the nearest defective matrix, but I didn't use her software very much. Okay, that's the story of eigenvalues finding their mates, and glad to be here. How much time have I used?
Plenty of time.
Yeah, okay. So questions? Yeah. Ilse.
So with regard to computing eigenvalues not as roots of polynomials, Wilkinson wrote a paper, the perfidious polynomial, which actually won the Chauvenet Prize for mathematical exposition.
Well, that's about the Wilkinson polynomial. People found eigenvalues by finding the characteristic polynomial and then finding its roots. And there was a lot of interest then in polynomial root finding. Wilkinson showed that was a bad idea. A, that was a bad idea to go on the characteristic polynomial. And B, he had an alternative method that didn't need the characteristic polynomial, namely the QR algorithm, and invented by Francis, but perfected by Wilkinson. And that's what we all use today. I had the idea of using the eigenvalue problem to find roots. So you set up the characteristic, set up the companion matrix and find its eigenvalues. That completely turns the table on the traditional method. And I didn't know whether it was a good idea or not. I did it because it means I didn't have to have a whole bunch of software. And Nick Trefethen showed years later that was, as long as you did balancing, that I was lucky, and that turned out to be a pretty good method.
I want to give a comment on this paper, which was actually started when all four authors were visiting me in Berlin.
Oh yes, that's right.
And it was very interesting. This was such a frustrating research because they tried to get the information what is happening when the two really meet about the second derivative, and this is still unsolved. And to see, I mean, this one case where they meet like a cross.
That's easy.
That's the easy part.
Yeah.
But to really understand what the perturbation behavior is in the second derivative, which actually was needed into the algorithm, and why the algorithm is so complicated, is partly for that reason.
Because of this picture.
Yeah.
So these two are not meeting in the standard saddle point.
Yeah.
They're meeting in a different way, and the derivatives that the optimization needed don't exist here, because this meeting is not smooth. Over here, another. Oh.
This isn't my question, but I did notice, as an indication of how times have changed from Wilkinson's day, that you made no distinction between kissing and mating. But
I was wondering about that title. I made it just in a spur of the moment when I had to do an abstract.
But my question
is, live with the title.
So I guess the Abo people find a non-symmetric perturbation, but presumably in a symmetric case like this, there would also exist a symmetric perturbation?
No, well, I don't think so.
Really?
No, the symmetric matrix can't be defective, it's a normal matrix.
So wouldn't there also exist a symmetric perturbation of the same norm?
Yes, it's exactly the same perturbation.
Yeah.
But it never becomes defective. It's the first time they meet.
So this software finds a non-symmetric one.
Yeah.
But in this case, there would also be a symmetric one.
Well, but that wouldn't be the nearest one.
Wouldn't it?
Yes, it is. It's exactly the same.
If you perturb both corner entries, probably.
It's not a defective matrix. It's
Yeah.
the first time.
Well, that's right. It's a double singular value. It's a double singular value.
You mentioned, was it Geer's method for the polynomial solver?
Laguerre.
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 Yeah. Because I remember Jim doing Muller's method for solving polynomials. And he always said he didn't really want to release his polynomial solvers because people would use them to solve eigenvalue problems. So I think none of them were actually publicly released.
My story, I made up the names Laguerre and Barstow. There were two methods. I don't remember what they were, but yeah.
I think it
Those
was
were two
Muller's,
methods around the
Yeah.
time.
I think it was Muller's method that was the other one Jim used. Yeah.
Well, that's too close to Moeller's method. I don't want to use that.